So Jefferson is going to be presenting on filtering guided waves for characterizing subsea permafrost. And you have the table.
Thank you so much. So my name is Jefferson Bustamante. I'm a PhD student at the Polytechnic of Montreal. This presentation was originally presented in the image meeting for the SEG. So basically, there is an abstract for that. My co-authors will be Professor Gabriel Fabien-Oulet, Matthew Duchens, and Dr. Ibrahim. The presentation is divided in three main sections. So in the first section, I will present the context, the problem statement. Then I will present what's gonna be the guided wave filter. And I will present an example of the denoising. And at the end, I will present the conclusion. So a bit of the context. So permafrost was formed in the last glacial period at the surface. So at the end of the glacial period, the sea level increases, locating some of that permafrost under the sea level. So nowadays that permafrost can act as a barrier for methane and CO2 reservoirs, and also can generate the conditions for gas hydrates to form. So if permafrost degrades, those greenhouse gases could migrate to the atmosphere, increasing the global warming. So therefore, evaluating the state of the permafrost is a crucial step for understanding its potential impact in global climate. So these plots are very similar to the work of Ensan in the last slide. So basically what is showing is that the ice in the pore space substantially increased the seismic velocity of the sediments. So we can notice that over the freezing point, the seismic velocities are basically constant. And between the freezing point and the euteric point, they will increase. And the way they increase will depend on the salinity. So Dr. Du in 2015, we created these plots. And she also transformed them to estimate ice saturation. We notice a trend where the trend is in between the ice model floating in the pore space and ice acting as cementing the grains. So knowing that in 2014, a seismic survey was shot over the outer continental shelf and upper slope of the Canadian Beaufort Sea. So that's the map of the survey. And the objective of the survey was to map and document the occurrence of subsea permafrost and gas hydrates. So for this presentation, we will focus on line 6, is this line in here. We notice that we have a well site in here where we have available some crystal cable velocity surveys that we will use for comparisons. About the technical parameters of the surveys, we have a streamer that contains 120 hydrophones with 12.5 meters spacing, and the source was a 1200 square inch gigant. Okay, so this is the stacking image. This is the stacking image. So the first thing that we can observe from the stacking image is that we can see the top of the ocean bottom. And we can also obtain the top of the permafrost. But after that, lower than the top of the permafrost, what we want to obtain is multiples that are hiding the identification of deeper reflections. For example, we cannot see anything that can be related to the base of the permafrost. So from previous studies in the area, we know that we have ice-bounded permafrost from 18 kilometers upward, and we have partially ice-bounded permafrost from 13 kilometers downwards. Between both of them, we have these diffractors, these many diffractors, and we associate this zone with patchy permafrost. From the velocity model survey, we can notice that the velocities increases just after what we relates to the top of the permafrost, keep until a certain point where it keeps more or less constant and it decreases. So our interpretation of that is permafrost forms in here, very consolidated permafrost, and then at the bottom we're gonna have a less consolidated permafrost, and then we will have unfrozen sediments. If we evaluate the shot gathers at the beginning and at the end of the line, that's shot number 7900 and 8275, we notice that the reflection multiples have interference from the reflections have interference from the multiples of the reflections from the guided waves in both shots, for the refracted arrivals and for the multiples of the refracted waves. We also notice that from the refracted arrivals, there is a amplitude decay with offset. Okay. So because in both cases, we know that we have guided waves, we transform our shot gathers into the dispersion plot. And in both cases, we notice the modal distribution associated with guided waves. So that's this kind of behavior. And it's observed from the beginning of the line to the end of the line. So we can say with that the phase velocity transformation is thus a good domain to design a filter for isolating guided waves. So the objectives of this presentation will be to present a method to separate recorded guided waves from the reflections and multiples. Will be to evaluate the method in shot gathers recorded on the Beaufort. So the filter is presented basically in this figure here. So starting from the shot gather, we transform it to the dispersion plot, that's a phase velocity frequency domain. And in the phase velocity frequency domain for a single shot, for a single mode, we're gonna select all the single pairs of phase velocity and frequency. Using this equation here, that is the same equation that you see here, we're gonna take the frequency and the velocity pairs, and we will apply a time shift. With the time shift, we will transfer to the FK domain. And the first thing that we will notice is that wave, that mode will be aligned close to the zero wave number. In the zero wave number, then we can apply a filter close to the zero wave number, reverse the time shift, and return to the shot gather. So we will repeat the procedure for every single mode. So an example of that is presented for the shot number 8275 in the seismic line 6. So this is the recorded shot gather, and this is the recorded dispersion plot. So after removing mode 0, the resulting dispersion plot is presented in here. You can see we have removed the first mode, and this is gonna be the resulting shot gather. The difference between recorded and resulting shot gather will be presented in here. So after removing the fundamental mode, we can say that we remove energy that is traveling at the velocity of the direct arrival. After removing the mode number 1, this mode in here, we not only are removing the velocity traveling at the velocity of the direct arrival, but also we are removing the energy that is traveling at the velocity of the refractive wave. So we continue removing modes, and what is happening is that we are increasing the frequency of the energy that we are removing. So we are removing energy traveling at the velocity of the direct arrival, is this one in here, and energy that is traveling at the velocity of the refractive waves. But with increasing modes, we are removing higher frequencies for that. After removing 6 modes, we can see in here that there are no more energy to remove associated with guided waves. And from the resulting difference, we can say that guided waves are here composed of the direct wave, the refractive wave, and the refractive multiples. And that agrees with the definition of guided waves. So if we compare the resulting dispersion plots, we observe that the filter accurately removes energy that is mainly associated with the modal distribution of the guided waves. In the shot gather, we can say that the primaries and multiples can be better identified after removing the guided waves. As, for example, in here. It's much better to identify. It's easier to identify details of the multiples and reflections at medium to high offsets. So that's why the arrows are in here. So in here you can see that there's a lot of noise that cannot let us know what is happening. But in here, when we come in here, we can see very clear what is the tail of the reflection or the multiple. So the filter short-guided that's a much better input for further processing of reflections. If we compare with the conventional FK filter, the first thing that we observe is that our filter is target specific. So we remove just what we want to remove, while the FK filter is very aggressive. So we are removing with the FK filter, we are removing the whole pipe of information. So we can also, surprisingly, we also notice that our filter is very, when dealing with aliasing. In here, you can see how the energy is removing for the aliasing. While the FK filter, if you want to deal with aliasing, you have to reflect the filter and come back to here. You will remove even much more information. So in the short-guided domain, you can say that both filters suffer from artifacts generated by the FK filter. So you can notice that in here, and you can also notice that in here. Reflections can be better identified at near offsets with the guided weighted noise filter. So in here, you have a much clearer image compared with this one in here. And linear events interfere with the tails of the reflections after applying the FK filter. That's what is happening in here. You have some linear events that don't let us see the hyperboles, while in here the hyperbole is very clear. And the tails of the reflections are better identified with our approach. So to conclude, we present a filter that sequentially attempts to remove guided waves mode by mode. On the Bio4C data set, the application of the filter showed that the guided waves correspond to the interference of the direct wave, the refracted waves, and the refracted multiples. Although some high frequency noise in the form of ringing is generated before the first arrivals, the filter can isolate reflect events. Filtered shots could be further processed with free surface multiples, denoising, and conventional seismic processing techniques to possibly map the depth of subsea permafrost and estimate its thickness. Okay, thank you so much.
Thank you, Jefferson. So just in the interest of time, maybe we have time for one question, then we move on to the next presenter. Okay, Matt, we'll do one question from Matt.
Well, it's not a question. It's for the benefit of my boss, Gilles, and for the others as well. I just want to say that the work conducted by Jefferson and SN is part of my project, which studies the impact of environmental impact of degradations, permafrost degradation. SN is working on the fundamental of the geophysical response, and Jefferson is working on the applied side of things, so using seismic, surface seismic methods. And both of their work are used to develop methods to remotely detect permafrost degradation at sea or for submarine permafrost, or also terrestrial permafrost. So that's put a bit of perspective on the work they're both conducting.
But even if your boss is slow, I got that. after 3 years, no, 2 years. That's yeah. But thanks for the big picture. It's for the benefits of everyone. Good presentation, Jefferson and Nation.